Right, good morning, Year 10. So what we're going to be doing today is we're going to be jumping forward slightly and looking at sound waves. Don't worry, we're going back to look at the other things we haven't done yet a bit later on. So what I would like you to do is quickly sketch these into your book and then identify which of these waves have the highest amplitude, the shortest wavelength, which sound wave would be the quietest, and which would be the lowest pitch. Okay, and I would like you to have a very brief explanation, so one sentence explaining your choice. So that'll probably take you about 5 minutes. So pause the video and start that off now, please. Okay, welcome back. So which wave has the highest amplitude? Now remember, amplitude is displacement from the center. Okay, so each wave would have, like, imagine a line going through the middle of them like that. Which one goes furthest away from the center? It is, of course, number 3. Okay, so that would be, or also form your explanation. Its displacement is furthest from 0. Which wave has the shortest wavelength? It is number 2. Okay, if you physically got a ruler out on your screen and measured it, you'd see the distance between those two waves is much shorter than between any other of the waves. Okay, which sound wave would be the quietest? Right, that would be number 4. Okay, because the volume of a sound is based on its amplitude. Okay, its distance from, or sorry, displacement from 0. Okay, and since the displacement from 0 here is the least, that would make this the quietest. And then which sound would be the lowest pitch? Now, the pitch of the sound is based on a sound's frequency. So high frequencies would be this, but therefore the one with the lowest pitch, the lowest frequency, would actually be, well, 1, but also 3. I believe, I don't know if these are the same length, I'd actually have to physically measure them. But there's 2 complete waves, so therefore they're probably the same, just with different amplitudes. But if I was going to push comes to shove, I'd say 1, but I believe 1 and 3 are probably the same pitch. Okay, but either one in this case would be fine. Right, so today, all of you should be able to investigate how sound travels through solids, liquids, and gases. Most of you explained an observation made during a Bell and vacuum glass demonstration, and a few of you understand the limits to human hearing range. The hearing stuff we're actually going to focus on next lesson. I really want to make sure you've got this sound, this understanding of sound correct. Okay. So we would have done a practical today, and we will do one when we come back. So, which of these particle models represents solid, liquid, and gas? Okay, hopefully most of you have understood basic year 7 particle physics. This, of course, is a solid. This one would be a liquid, and this one would be a gas. But we need to look at the features a bit more in a bit more detail. And so I am going to ask you to very quickly sketch these into your book. Again, you might want to put them in the sort of order that you're used to. So solid would be number 1, liquid in the middle, and then gas would be over here at the end, number 3. Okay, so quickly pause that, and then we're going to talk about what we would add to our model in order to make it make sense. Okay, welcome back. So, talking about solids first, the thing you'll note about solids or particles in a solid is the particles are very, very tightly packed together. They're very dense, which means if sound can move through solids, then we would expect sound to be able to move through solids relatively quickly, because what happens is the density, the fact that the particles are very close together, means that sound can be transferred very easily through these particles because they are so close together. It's like tiny billiard balls knocking into each other and going bang, 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 like that, transferring sound through a solid. Liquids, you can see, they're also reasonably dense. They're reasonably tightly packed together. So we expect sound waves to be able to move through liquids also relatively easily. They're not quite as good as solids because obviously you can see there are small gaps between the particles, and overall this makes them slightly less dense, which means sound isn't transferred as easily. And then of course gases, if a sound wave was transferring through a gas, which is what we're used to because we hear sound through air, the sound waves don't travel efficiently at all, because as you can see there's big gaps between the particles, so they'll knock into each other, but the transferring of sound is not efficient. That's why in sound, even if you scream at the top of your voice, you can probably only hear someone maybe 100, 200 meters away clearly. Whereas if you had the same conversation, say underwater, you'd possibly be able to hear someone up to a mile away. And of course, people can hear explosions and things through the ground for several miles. In fact, whales have such loud voices for their whale song. They can hear each other over hundreds of miles through the water. Okay, right. So can you just add a quick little footnote about how the density of the particles affect how well each transverse sound? Right, I'm also going to try and quickly find a YouTube clip, which would be an assignment, which demonstrates how well sound moves through each of these mediums. Okay, so I want you to think about how we could use this this equipment in order to work out the speed of sound through solids, liquids, and gases. So you've got a stethoscope, a beaker, your hands, a tuning fork, a table, and some water. I think what you'd use a stethoscope for, the tuning fork, the table, why table, the beaker, some water, maybe those two are linked. Okay, how would this work? Just pause for a moment and think about how you would do this. Okay, so this is how the investigation would have actually gone down, and hopefully we'll get a chance to try this in class. So we're going to investigate whether sounds travel best through solids, liquids, or gases. So you put a stethoscope on the bench, other person knocks on the desk. So what that means is, can you hear the sound clearly going through a solid? Then you put the stethoscope in a beaker of water. You'd actually need quite a large beaker for this. Partner knocks a tuning fork on the desk and then places it in the water whilst it's still ringing. Can you hear it then? And then you hold the stethoscope up in the air. Your partner claps about a meter away, and you can see which was the loudest sound and which was also, sorry, didn't mean to do that, loudest sound and which was the clearest sound, or sorry, the quietest sound, based on that. So it's a very, very simple experiment, but it does give you an indication of how well sound moves through the three different mediums. Okay. So why do sounds travel fastest in solids? What is a vacuum, and how would a vacuum affect sound traveling? Now, hopefully you know what a vacuum is. A vacuum is when there are no particles. So if there are no particles, would sound be able to actually travel through it? What I did was I actually posted in this lesson a clip from Star Wars, and it's got all the lasers going off, going pew, 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 pew. We don't need to see that. We can work out what is scientifically wrong with the clip. And the bottom line is, right, well, in space, there are no particles. So every explosion that you hear, every laser being shot is actually completely incorrect. It's added sound effects. You wouldn't hear that at all. Because there are no particles to transfer the sound, you would hear nothing. And if you go into assignments, I put on another link from YouTube, demonstrates this very clearly. So what you've got is a bell in a jar. You suck out all the air, you can hear the sound disappearing. The bell is still ringing, but you can't hear it because there are no particles. So what I'd like to do is, once you've watched the video, pause this, draw this, so you've got a bell in a vacuum jar, and explain why, as you remove the air, you are unable to hear a sound. That'll only take you a couple of minutes. Okay. Now, welcome back. This part you do need to pay quite close attention to, because what we need to understand is how good the range of human hearing is. So, just to give you an example, okay, this shows all the different sort of sounds, okay, and the lowest sound that human can hear, so the one with the longest wavelength, the lowest pitch, okay, lowest frequency is 20 hertz. That's feel like a really low rumbling kind of sound, okay, barely audible. And then what we can do is we can hear pretty much every single range up to about 20,000 hertz. Okay, so just to give you an example of this, my plan was to actually be playing high frequency sounds through the speakers in the classroom and see if anyone actually noticed. But just to give you an example of this, okay, firstly, you need to be clear about this and make this big and clear in your book. Humans can hear from 20 hertz up to 20,000 hertz, also 20 kilohertz, okay? So just to give you an example, I have an app on my phone that shows this, and I can play you various sounds when the pigeon outside stops making a noise. So I can actually hear this. Hold on. Okay, so right now, my phone is putting out 30 hertz, which is the very lower end of what is audible, and most of us probably can't hear that. But if I put this up and hold it to the speaker, you might start to hear a sound. That's 138 hertz. Just listen carefully. Okay, moving up slightly. That's 788. So we're not even at 1,000 yet. So we're only nearly a 20th of the range that we can hear. That's nearly 2,000, so 1,910 hertz. That's about 5,000, so about a quarter of the range now. That's 10,859 hertz. So again, very high pitch. You probably still can hear that. Okay, that is 19,499. So that's at the very upper range of what human beings can hear. Now, listen carefully. I can't hear that at all, but you might just be able to with your young ears. Okay, going to move it down slightly. So that's, oh, hang on. Okay, that's 14,000. So that's like 3/4 of the way up. Okay, I can just about hear that. Listen carefully. You might be able to as well. Okay, stop that now. Anyway, the point is, human beings, we have a range, and anything beyond this range of 20,000 hertz we call ultrasound. Okay, so you can see that considering the range of sounds, it's quite limited. Really important to note, I wasn't changing the volume when I was doing that demonstration. It was exactly the same. Even though it seemed to get quieter, it really wasn't. The volume, the actual amplitude of the sound remained completely consistent. It's just at the very lower end and at the very upper end, we find it quite difficult to hear. Okay, and as you can see, the sound continues on, and we simply can't hear it. But there are many animals that can. So, for example, oh, also I should point out, as you can see, the scale isn't linear because look, there's 10, a gap of 10 there, and there's a gap of 90 there, and a gap of 900 there. So this is a logarithmic scale. This is not a linear scale. I should point that out. But look, there's humans. We can hear from 20 to 20,000. Elephants, they can't hear high-pitched sounds that we can hear, but they can hear much lower-pitched sounds. That's why elephants often make that deep rumbling. Dogs, you may be aware, right, they can't hear low-pitched sounds, but they can hear actually very, very high-pitched sounds. So there's 20, there's the range humans can hear. Dogs can hear beyond that. Okay, that's why a dog whistle works. But you can see almost double. We can only go up to 20,000. They go up to 45,000 hertz, a very high frequency. Cats, Even better, they can go up to 65,000 hertz, so they'll hear really high-pitched sounds. And then you've got other creatures. Mouse can hear up to 100,000 hertz, so really high frequency. Bat can hear up to 120,000 hertz. Blue whale can't hear really low pitch, but can hear very high pitched sounds. And then dolphins up to 150,000 hertz. Dolphins also use high frequency sound to hunt for food because high frequency sounds produce the best echoes. And of course, dolphins hunt by echolocation, using echoes in order to find their food. Right, so we're going on to hearing next lesson. So it might be a good idea to very quickly copy out a simple version of this. If you would prefer, then just description describing where humans fit into this range. But most importantly, you need to have an idea of this hearing range for humans, 20 to 20,000 hertz. That is the range of human hearing. Anything above that is called ultrasound. High frequency sounds give much more distinct echoes. So creatures like bats, whales, and dolphins use ultrasound in order to hunt or navigate. Okay, they're able to access those very, very high frequencies. Okay, they can hear them because they need them. Okay, right. So first things first, what I would like you to do is firstly, there are the 2 videos in YouTube. You need one that shows how sound waves move through particles. So that's the first link. The video is actually 20 minutes long, but you only need the first 6, 7 minutes of it. There's a bit of an introduction, and then it goes to the demonstration about how sound moves through different mediums. Then the second link shows how what happens to sound as it is removed from a bell jar. Okay, so those are 2 links which are going to be in assignments. So the videos are probably take about 10 minutes in total if you watch both of them. And then there are a series of questions on sound, which I would like you to do, which is also going to be in assignments. There are 17 questions, 5 questions, but they're all broken down into parts. The only question that I think you might not be able to do is question 4D, because it does relate specifically to ultrasound and echoes, which we haven't done yet and we're not going to do for a couple of lessons. Okay, so 4D, if you get a bit stuck, I mean, you can have a go at it, but if you do get a bit stuck, just skip it off and have a go at the rest of them. Right, so good luck, Year 10, and as always, I'll be online to help you out if you need it.